let's start. My name is Sobhan Kazempour Ishka, as we have mentioned. The title of my presentation is the Cosmological Aspect of Massive Gravity Theory. In fact, this is my PhD research, which I have been working throughout 2 years under supervision of Dr. Amirza Akbariye, and my co-advisors are Dr. Hossein Mutawalli and Li Shao. In this presentation, initially, I will talk about introduction, and I will introduce our motivation. In the next step, I will review the massive gravity theory. Actually, I will review the problems in this theory, and I show the alternative approaches. Moreover, I will present the new extensions of massive gravity theory, and I indicate their cosmological aspects. In the following, I show some of our results and calculations. Very briefly, finally, I will propose some possible questions. As you can see that all of us know that the accelerated expansion of the universe as observed by several cosmological data such as supernova, 1A, CMB, and baryon acoustic oscillations, it is obvious that the dark energy has been introduced as an unknown form of energy in order to explain the accelerated expansion of the universe on the largest scale as one of the solutions. On the other hand, the massive gravity is another way, and this theory tries to make a connection between general relativity and the quantum gravity. In the following, I try to review the massive gravity theory. As you can see here, in the 1939, Fiers and Pauli introduced the first consistent linear theory of massive gravity. This theory describes the massive spin-to field in this action. As you can see, the H mu is a symmetric tensor field. It was the first attempt in this way. In the 1970s, Van Dam, Weltman, and Zakharov found that the Fiers-Pauli action in the limit of m towards 0 does not reduce to the general relativity, and it was known as a VDVZ discontinuity. In other words, if we consider m equals 0 in a linear Fiers-Pauli action, we cannot reduce to the general relativity. In fact, as you can see in the picture, there is difference between the bending of light in the Fiers-Pauli action in the limit of m towards 0 and the general relativity. In the 1972, Einstein showed for avoiding the VDVZ discontinuity, we should consider a nonlinear Fiers-Pauli action instead of a linear theory. This way, the prediction of general relativity recover at a small scales. In the following, in the 1972, Walt Desert mentioned that there is a ghost instability in any nonlinear completion of Fiers-Pauli action. In addition, in 2005, Reminelli and Hamed Arkani confirmed the result too. Anyway, suddenly in 2010, Diram, Gabadadze, and Tolly revisited all analyses, and they found that we can have a theory of a nonlinear massive gravity without any ghost in the certain decoupling limit. And here you can see the DRGT action. In the following slide, I will talk about it. However, it should be mentioned that the DRGT theory does not admit a flat FLRW solution, and there are instability in this theory. This is the reason why we are looking forward to an alternative theory. Therefore, some alternative ways have been introduced. As you can see, the first one is that we consider inhomogeneities and anisotropic universe, but according to several observations, the universe is homogeneous and isotropic on the large scale. Another alternative theory is a massive gravity in we consider the massive gravity in higher dimensions and there are several research and investments in this field. Another way is considering additional degrees of freedom in the massive gravity theory. For the tensor one, we have the bigravity and multigravity, and for the scalar one, they have the quasi-dilaton and extended of quasi-dilaton and mass varying and so on. Finally, new massive gravity in 3 dimensions is another way in the massive gravity. Here you can see the possible research that can be done in the context of massive gravity. The first one is introducing the new extensions of massive gravity. The second one is studying the cosmological data to constrain the mass of graviton and imposing constraint on the parameter of new extension of massive gravity theory. Furthermore, we can study cosmological and astronomical aspects of several issues in the context of massive gravity theory, for instance, gravitational wave, black holes, pulsars, and so on. In the following, I introduce some of the new extensions we introduced and we worked. As you can see that concerning the new extensions of massive gravity, it should be mentioned that we introduced the Gauss-Bonnet dilaton massive gravity, and this work is published in the PRD. In the second one, we introduced the tachyonic massive gravity. Fortunately, this is published in Physical Review D2. We worked in another study, another paper, and we introduced the cubic Galilean massive gravity, and it was another extension, and it was published in Physical Review D2. In addition, we have been working on the new extensions, which are a non-minimal quasi-dilaton massive gravity, Brans-Dicke massive gravity, and another new extensions, and so on. For instance, here I'm showing one of our extensions, which is the Gauss-Bonnet quasi-dilaton massive gravity. Here you can see that as you can see that the quasi-dilaton DRGT massive gravity is extended by Gauss-Bonnet term. In this action, the R is a Ricci scalar and lambda is a cosmological constant, and this part is related to DRGT massive gravity, and MG is a mass of graviton, and this part is related to quasi-dilaton, and this new part is related to Gauss-Bonnet term. Here, the U is a potential, and as you can see, omega is a dimensionless constant, and the sigma is a quasi-dilaton scalar, and kappa and trace of it is the building block tensor. The chi sigma is a coupling function, and as you can see here, the kappa is defined according to this equation, and F is a physical metric, and G mu alpha is a dynamical metric. And this is the Gauss-Bonnet terms. In 4 dimensions, if we consider the chi as a dimensionless coupling constant instead of a coupling function, the Gauss-Bonnet term does not contribute to the gravitational dynamics because the Gauss-Bonnet is the total derivative. So we consider it as a coupling function. And here you can see some of the relations which have something to do with the potential, and that's it. In the following, we find the total Lagrangian of this new extension. The part of Lagrangian is related to DRGT massive gravity, and this part is related to the quasi-dilaton, and this part is related to Gauss-Bonnet term, which we added by us in this research, and the other parameters are defined as you can see here. In this stage, by varying with respect to F, N, and sigma and A scale factor, we obtain the background equation of this theory, as you can see. Also, there's a Bianchi identity which relates the 4 equations of motion. So one equation is redundant and can be eliminated. In the self-accelerating solution, we describe the solutions very briefly. Actually, we are looking forward to finding, to explain the self-accelerated expansion of the universe using this new theory. The constant solution of X, after some calculation, we find this equation, and the constant solution of X lead to the effective energy density and behave similar to a cosmological constant. If we consider an expanding universe according to the part of this equation, the right-hand side of the equation will decrease. So after a long enough time, X lead to a constant value, saturate X, which is a root of left-hand side of that equation. Note that two of solution are X equals 0 and X equals 1. Because of the strong coupling and inconsistency, they are unacceptable. Therefore, we have therefore, there are 2 remaining solutions, as you can see here. And after some analysis, the H square is obtained here. Finally, we found the RSA for the 2 cases. In the first case, the first derivative of chi sigma is a constant, and the second derivative is 0. In the second case, this is not 0. As a result, the RSA1 and RSA2 can explain the self-accelerated expansion of the universe according to the new parameters of the theory or theory. In this slide, you can see the tachyonic massive gravity theory. This is another extension we have worked and we have done it. Here you can see the actions of this theory, and this part is a new part. V is a tachyonic potential, and sigma is a tachyonic field. And other equations are similar to first case. In the following, with as I mentioned before about the first case, here we calculate the Poincare function, and this part is related to tachyonic part of this theory. Similar to first case, we by varying with respect to physicoelectric lapse function and so on, we calculate the background equations. And about the self-accelerating background solutions, because some of the processes are similar, I disregarded this part. After some calculations, we find the RSA for this research according to this equation, as you can see. And here, I would like to talk about the cosmological test. I think that one of the most important things is testing and imposing some constraint on the new parameters of the theory. And here we use the supernova 1A data, which consists of 557 data. And here you can see this is the module distance, and here the DL is the luminosity distance. After some calculations, and in order to find the best value which to be fit with the data, we do some calculations, as you can see here, by minimizing the equation, which consists of some observational data and the parameters of the theory. We find the best value which to be fit with this cosmological data. And this part is related to one of our publication. In this stage, I should say that there are some options for study in the context of massive gravity. As you can see, we can consider the perturbation analysis. In terms of perturbation, we can investigate dispersion relation of gravitational wave, which is related to the mass of graviton. About the vector perturbation, I should say that this perturbation is not very important and does not have any role in the large scale formation. Concerning the scalar perturbation, it should be mentioned that the scalar perturbations are induced by energy density in homogeneities. These perturbations are most essential because they show gravitational instability and may lead to the formation of structure in the universe. Moreover, the other aspect can be considered. For example, we can study the black hole. We can find the new solutions in the context of massive gravity theory. Moreover, the geodesic motions of the particles and light ray can be studied in the black hole in the context of massive gravity. Also, the accretion disk around the black hole in the context of massive gravity can be studied, and we have done one of them. And in the following, I show our result. Before that, here you can see the tensor perturbations analyses which we have done for the Gauss planet with dilaton massive gravity. Actually, we calculate the dispersion relation of gravitational wave. In order to obtain the mass of graviton for this theory, we achieve the action quadratic, and after some analysis, we obtain the dispersion relation of gravitational wave for two cases. And actually, the main result of this part are modified dispersion relation of gravitational wave. We present the propagation gravitational perturbation in the FLRW cosmology in the Gauss planet with dilaton massive gravity. It is interesting to note that the propagation can be tested with cosmological event, notably by gravitational wave observation. Here you can see the tensor perturbation for the tachyonic massive gravity, and here you can see the gravitational part of the quadratic action, and the tachyonic part is obtained here. Finally, we find the dispersion relation of gravitational wave for this theory there too. As I have mentioned before about the accretion disk around the black hole in DRGT massive gravity in the context of massive gravity, we consider a static and spherically symmetric black hole solution in DRGT massive gravity. As you can see here, FR is defined, as you can see. M is a mass of black hole, and the MAG is a mass of is the graviton mass, and alpha and beta are new parameters of the theory. In order to avoid some problems such as strong coupling and superluminality and so on, we consider the physical metric in the different ways, and it is worth pointing out that the graviton mass can be considered as a cosmological constant in the self-expanding cosmological solution in the massive gravity. We should pay attention that if we consider the mass of graviton equals 0, we have the Schwarzschild black hole. The graph here show that the profile of FR, the green and blue curves show 3 event horizon of the black hole in DRGT massive gravity, and the red curve is related to Schwarzschild black hole. And you can see the differences between the event horizons in standard general relativity and the massive gravity theory. And this research and our research, it has been reviewed in Physical Reviews C, and I hope it will be published as soon as possible. Also, the geodesic equation of the massive particle can be calculated. The equations can be described, the dynamics of the system, and we obtain all of them. Using the dimensionless quantities, the effective potential can be obtained. And in the following, we obtain all the parameters of the accretion disk of the black hole in the context of massive gravity, the specific energy, the specific angular momentum, and the angular velocity. As you can see here, we plot the effective potential and the location of stable circular orbit for the 2 cases, and all details of this research can be found in our paper. And we try to show the differences between can be seen in the standard general relativity and massive gravity in studying accretion disk of black hole. Here you can see the possible result. The first one is we can introduce the new extension of massive gravity theory. We can present the equations of motion for these new theories, and we can show their evaluations. We can discuss the self-accelerating solution of the theories, as I showed some of them. Showing astronomical and cosmological predictions in these theories is a way for testing these theories. For instance, studying and analysis of the dispersion relation of gravitational wave, finding the additional polarization, and so on. Furthermore, we can compare our theories and these new extensions with cosmological and astronomical data. This way, we can impose some constraint on the new parameters of the theory, and it's very valuable for us. The possible question can be, should be considered is that, what approach can be considered for introducing new extensions of massive gravity? Has Bolwer-Diezer ghost been checked in new extensions? And the third one is, how can be possible to find a unique theory as massive gravity, as we have there are a lot of extensions of massive gravity theory, and finding the unique theory in massive gravity is very crucial. And I think this question has something to do with the first question. If we find the correct way and approach for introducing the new extension, we can find a unique theory. Finally, how we can determine the mass of graviton, and how that testable way for checking that mass can be found, and it's another important thing. Okay, thank you very much for your attention.
Thank you, Sobhan. I should also mention that Sobhan has helped a lot in holding this conference and has been in charge of many things. So I have to say special thanks to Sobhan.
Thank you very much.
Any question?
Okay.
Any question?
Hi, I have a question. I don't know if you can hear me.
Yes, I can hear
Can you hear me?
Yes.
Please, of course.
Nice to see you.
Hi, Sobhan. Very nice talk. Very nice talk. You mentioned your analysis for the tensor perturbations in the Gauss-Bonnet quasi-dilaton massive gravity. Have you looked at the scalar perturbations? Because that's usually where there are some issues arising in these quasi-dilaton-like theories. Have you done that? Or?
To be honest, this is the next project we would like to do, and it would be very good if you accept to join to this project, and and we will be very glad. And I think that it would be very valuable. We have tried to do some calculation this way, and that's it.
I see. Yeah. One other thing, I think you, in the Stuckelberg equation, you find that it goes like 1 over scale factor to the 4. And then you say that the right-hand side should go to 0 eventually, and you take the fixed point solution, I think. So that's also one point where you should be careful, because people have found in the extended quasi-dilaton theory, we were mistaken to do the stability analysis on the fixed point, and we thought there was no ghost. But when other people have done the calculation away from the fixed point, they showed that we were mistaken. So that's also one thing to keep in mind, just in case, because these theories are really difficult to work with. They have too many degrees of freedom. So you go for simplifications, but sometimes it's easier to convince yourself that things are fine. But yeah, I don't know. Of course, I'm not saying that your theory is wrong. It's just that this is something that you should check, definitely. Yeah.
Thank you very much. We should take this issue into consideration. Thank you very much.
Thank you. Other question? Okay. I have to tell you that the next meeting will be in an hour and a half. Our next speaker will be Dr. Amir Gümrükçoğlu.